right, guys. So this is the second week of the on the capstone. Let me just make sure I got the right table open. Oh, it's this one. Yes. All right, guys. So so last week, I told you guys we'd be working with this Dream Challenge leukemia data set. You guys will be working with that on your own. Meanwhile, we'll play with like a sort of toy problem, a little bit easier one. So before we jump into that, I wanted to touch base with how those calculations are going, because it's kind of like a big, it's like a big thing that's going to take more than a week to finish. So we kind of figured at this point you should have, definitely have the data by now and have begun to like format it. So we'll just start. Like, does anybody have any questions so far? Did anybody have any problem getting the data? Have you guys begun to look at it? Yeah, no issues. Yeah, so okay, I'll take a few seconds to some of the things that I noticed when I started working with it. I won't give any answers away or anything like that, but from what I took away from it was you really should try to get the data like programmatically, right? I showed you guys how in Kaggle you can use like an API token. You could do the same thing here after you set up your account and whatnot. And so I'll take like 2 minutes or so to talk about how Synapse uses APIs and how you can log in programmatically in a safe way. But as for today, with our toy problem, we pretty much have hit, we're going to hit all of these points, except for maybe this one I was noticing. After we do some feature selection, you want to settle on a model. And the process by which you do that, I don't think I've really gone into too much detail. We simply just pick one and then start training it. So, so if I may take a minute here, once you get to this part here, I suppose what I want you guys to do is take your data, decide on how you're going to partition it, and if you feel you have the luxury to do so, reserve a discovery set, right? And you're going to use this discovery set to get a handle on the potential, the prognostic potential of certain models, right? So you'll have like a panel of models that you want to try out. You're not going to train them. You're not trying to get, like the performance that your final performance or anything like that. You're just going to ask of these models, which one has the highest potential to give me the highest performance. And so that's what you use your discovery set for. And a good measure of this, especially for binary classification, is the area under the ROC curve. Okay, so we'll talk a little bit about ROC curves today, but the idea is that you'll pass your model through, you pass your discovery set through these models, and then rank them by their AUC. Okay, so that's one strategy to pick a model. The other strategy is pick them all and then put them in some like stacked ensemble sort of setup, and we'll do that today. Okay, so that was my 2 bits on that. Everything else we're gonna talk about today. It sounds like you guys got the data, so I'll take a minute or two to talk about the API. So so the Synapse folks, they have a client. It's an Python package, right? They have one also for R and Java and even command line tools, but we'll be using this Synapse client, well, you can use it to access the data programmatically within your script. So you can follow along in your own notebook on your own time, but I'll just sort of quickly run it for you guys. So here I just installed it. And I mentioned here you have to, of course, have an account. You need to register. And the syntax for this thing is dirt simple. It's called it's the login function, right? So you would create this Synapse object and then do login, and it's going to follow a certain set of procedures. One, it's either going to check for you pass it your email and password, and then it'll log you in, or you can look for this API token that's on your machine, kind of like what we did in Kaggle, like you put it in your home directory. So it's the same thing. It's a file called the synapse.config file. You'll put it in your home directory. You could read the directions here a little more. And I even put here a link to a default config file. So you just enter your credentials like that and then save it in the appropriate place. And you know, it should now log you in without having to pass any parameters into the login function. Okay, so that's the safe way to do it. The easy way is to use the login function and just type in your email and password, right? So like, this is not safe, especially if you like were to save this notebook and then put it on some repo somewhere. So really try to use a token, but for everyone here, I guess, if you want to do it the hacky way, you just call this login function here. Oh, how I did import GetPass. Yeah, you can use a GetPass so that it's like commented out, not commented out, but it shows us like little asterisks. But you have to do that like in person, right? You can't just run the script like end to end. It would interrupt and ask you to enter your credentials. And ideally, if this is some module in some bigger pipeline, we can have you like manually enter stuff. So really go with like tokens. But yeah, you could use GetPass. So just to get you going, if you haven't already, you just so we import the client, we create the object, the Synapse client object, and you'll uncomment this, log in, and then enter your credentials here, and then just use the remember me true. This is going to create that config file for you and save it. Once you do that, immediately erase all your email stuff before you like, by accident or like muscle memory, just save the script. Don't save your passwords ever. And then you, if you did it right, it made the config file for you and it's saved on your computer. And then you can just check if your credentials were saved. You just log out, log back in, passing it nothing, and it should work. So I already made a config file, so I don't type my credentials in front of everyone. So right now I just ran the client and created the object. I didn't log in. If I log out and you haven't logged in, it just ignores it, and it's going to attempt to log in again, and it found me. So great. Okay. So to download the data, it's pretty simple. It's this. If you actually go to the website, they'll give you a code. I'll do that for you guys, in fact. So if you go to the data set, access the data, right here, download options, you can go to programmatic options and then just pick the Python one. And here, it's the code is given for you. So it's using this sync from Synapse tools. Yeah, so yes, that's what I'm using here. You can override the default place where it stores the data. I think it's on your home directory, which is like a mess for me. Maybe for you guys it's clean. So what I did was I just put it in a data folder that's right next to where this notebook is. Okay, and it's going to download it all and run. It ran it, and maybe I have. Well, you'll find that there are four files. We're going to be using these. The training and score. This is a training and testing data sets. And yeah, so now I'll just show the head of the training data to make sure that it's. Oh, I didn't run the I wrote this weird. Here's the setup is all down here. Let me just import all my packages. All right, I think it's done. Yeah. No, geez. GitHub and run this. Okay, I think it installed everything. So there you go. So your data is going to look something like this. This is only the first 5 rows. Here you see some of the clinical variables, and at the end you have the genomic data. All right. So that's my 2 cents on how to access the data programmatically. Let's move on to our toy problem. Okay. Yeah, and feel free to jump in, guys, to let me know if there's something you want me to like cover in more detail or do differently, because there's a million ways to, like, you know, skin a cat, right? Like, so the analysis here, we admit we've pretty much done most of the work already, and that was the data processing. Once you get to the point where we are training and you've already decided your model, it's really just hit train, right? And you kind of have to put your money where your mouth is and commit, right? What I've chosen to do here is, well, I need to re-download all my data because this is like a virtual thing. So this is all from last week. I've put in the code that we wrote last week together. So we got the training data. We saw that there were these call functions we wanted to get rid of. We figured out how to do that. We got rid of them. We noticed that the rows and columns are inverted. So we just transposed it. And we saved the ascension numbers because we're going to need them later. And got rid of them because it's bookkeeping data that we don't need. And finally, we get some data that looks like this, right? Our observations are in rows and our features are in columns. There are 7,000 genomic features in this data set. So we definitely have to do some dimension reduction, right? The labels, oh, we just codified the labels. We did this last time. We treated the missing data. You're definitely going to have to do this in your real data. Okay, so we chose to do PCA for dimension reduction. PCA is like the first thing anyone ever tries. It's like the most common. For any problem that's worth solving, it rarely works. So you'll see a lot of papers that'll say, our method, like we compared it to PCA. Yeah, lol, yeah. We compared it to PCA and it's like so much better. And you're like, well, I mean, yeah. But for like pedagogical reasons, it's a great way to get your head around a dimension reduction. I think the audience here today is like really comfortable with that concept, so we can kind of blow through it. So last time we used a scikit-learn, right, to do this. They have the PCA in their decomposition as part of their decompositions, and we chose to compress it to 10 dimensions, right? I mean, so here we created the PCA object and we defined the number of dimensions. With PCA, this is really important. you have to scale the data. Most times, and I think scikit-learn does it too, and the R equivalent, most time it'll do the scaling for you, but you really should get in the habit of doing it yourself because, yeah, you don't know what flags have been turned on and off. If the data isn't mean-centered with unit scaling, then the principal components are not gonna, well, they're not on the same statistical footing, right? It's basically doing like a distance measure, right? And if one coordinate varies a lot more than another one, then guess what? Your principal component is going to be dominated by this one feature that's highly variant. So yeah, always scale your data. So here's another thing. I don't know if I mentioned this last week, but when we scale our data, you're allowed only your training data. Often we see people, let's say they'll scale all of their data, their training and testing data, and that's technically not right. The testing data should be completely divorced from this analysis, right? So the proper thing to do is, here I'm fitting the data to the training and going ahead and transforming it. I'm transforming the training data and saving it as X scaled. Okay. And then I need to transform into the PCA, the PC representation, right? So I use my PCA object and I'm gonna, fit this object on the scaled data and then go ahead and do the transformation. So the result is the X trained data, but in the PCA representation. Okay, now that you have your scalar fit and your PCA object fit, you can use them to transform your test data, right? So you apply that fit scalar, it was fit with the training data, you apply it to your test data. And that's going to give you like scaled test data. I didn't save it because it's only transient. I don't really need to keep it after I use it but you put in that scaled test data and you go ahead and transform it into the PCA representation. And this is what I save as X test PCA. Okay, so this is like the proper way to do it. Just go ahead and run it. And you can see here, I just print out the dimensions of it. It's 38 samples or observations and now only 10 features, right? 10 dimensions. Great. Okay, but 10 is a magic number, right? So now here's where like today's work begins. So we need to like decide how many principal components to use moving forward. There's the sort of gut reaction is to say, well, let's just try a few, put it in the model and see how it performs. And if it doesn't perform well enough, then I'll, increase the number of principal components. Yeah. And you can even say sometimes like, and I'll also be really good. I'm only going to look at the training data, right? I'm not actually going to look at the test data until I've figured out how many. You can do that if you restrict yourself to some discovery set. But what are you going to do when it comes time to feature selection? You already burned through your discovery set, right? So it's best to do all the, technically we're still in the data processing bit, right? So before we move on to training, you want to like decide how you're going to process your data before you move on to any kind of model development, right? So let's avoid stuffing this into a model and seeing how it performs. Okay, so so motivated by like the science or whatnot, you can say something like, let's try to capture 80% of the variance of the data. How many PCs do I need? That's a perfectly legitimate and probably like the most common technique people use to decide how many principal components to use, is to say 80%. Does that make sense, what I've said so far? Yeah? So, so when you write up your paper, you'll say the number of, you'll say 80%, and it's one of those magic numbers that people, that, you know, it isn't like a sort of hard pill to swallow or whatever, right? Okay, so we're gonna do that here. So here I'm creating a PCA object here, and I didn't define the number of components. I just gave it a seed, and I like instantiated PCA, right? I made a scalar again. I don't know why, since it's already, oh, because it's been fit. We need to erase it. Okay, and I went ahead and did the same thing. I scaled my X data on the training data and got and fit the PCA. I fit the PCA on the scale data, but now I didn't restrict it to the number of dimensions. So this X-trained PCA in principle has all 7,000 modes, every 7,000 principal components. Okay. So the PCA object, if you look in the scikit-learn and you look at its attributes, in fact, maybe we can do that now. That's learn PCA. You can see here in its attributes this, right? Explain variance, and so you can pull out how much the variance is explained by a certain number of components, and like the first 10, the first 100, and the first 1,000 components. So we're going to go ahead and use this explained variance here, and this is going to be for it's the explained variance per degree of freedom, right? Per principal component, and I want to add them all up, and that's going to be our total. Okay, and now what I want to do is I want to march along every principal component and pull out the amount of variance explained, and then display that as a ratio of the total variance explained. Does that make sense? So if the first principal component explains 20% of the variation, and the total, for some reason, the units are weird, but it doesn't add up to 100. It adds up to, you know, like 1,000, I don't know. Then the amount of the percentage, right, the fraction of variance that is explained by the first principal component is that value, like 20 divided by the total 1,000. You get what I'm saying? And then we want to know how much is explained by the first two principal components. So we need to keep along this like cumulant, right? We need to keep accumulating what the variance is of the current principal component and all the previous ones. Okay, and we're going to use like a while loop to do so. So here's where I ask you guys to help me write this code here. So what I'm looking for is a while loop, and it's going to go over all the principal components, and I want it to stop once it reaches 80%, right? Once the total variance is explained, passes 80, and then I stop, and that's the number of principal components to use. So yeah, so feel free to enter that in the chat whenever you guys can get it. First of all, like, let me know if you like, what is he talking about? Ooh, the for loop, yeah. Yeah, you don't even have to use loops. Loops are terrible, but yeah. Sure, you want to do it? We can do it with a for loop. I like a while because it like you break out of it. Whereas a for loop is like, while a condition is true. Yeah. So the while loop, right? It's like while some condition is true, right? So while some condition, oops, I'm writing in the chat. While some condition is true, right? I don't know what this condition is. This condition is something like while. Any guesses from folks in the audience? So I've initialized this loop to like, 0, right? We're considering zero principal component, and so far the running sum of variance is 0, and we start right with the first one, and then we calculate the variance and accumulate it, right? Yeah. All right, what's this? Okay, so while cumulative variance is less than the total, 80% of the total, okay, accumulate the variance, right? MP delete. Oh, you're deleting.
Yeah, I have a question.
Yeah.
When you check PCA.explained variance, they're in descending order. I'm not sure why. So
descending order. Yeah, the first principal component explains the most variance.
Yeah, so that was my reason, basically.
Yeah. Oh, so if you delete the
first one,
then you move to the next one. You can do it that way, but you're carrying an index there, right? NPC.
Oh yeah, I can definitely reach that and get that. Yeah, it makes more sense.
So, but it's definitely like that. I love the plus equals notation there. So yeah, you got something like your condition is, yeah, that's right, your condition. So the condition is, well, the cumulative variance is less than or equal to like total times 0.8, right? Like 80% of the total. Then if it's still less, then keep looping, right? So we get the PCA dot, I'll just copy this. The variance of NPC, right? Because we start out with index 0. Yeah, so we want to add this to the cumulative, right? Yep, plus equals. Yeah, so it starts off with nothing, we add the first one, and then we add the second one and the third one. Yes. this should work. And then we need to increment the index, right? NPC plus equals 1. I think this will work. Okay. Is everyone's great with that? That's a very elegant way to write it. It's written in 2 lines. Yeah, and then right here, we're just going to print, like, once we break out of this loop, NPC is going to have some value. And then we're going to say, this many features explains 80% of the variance. So yeah, and then it's like, we started with this many features and now we have this many. Fine. It's unnecessary, but verbosity. 21 features explain the variance. So NPC is now 21. Okay, so here in this next one, that's a great job. Here, I want to plot it. So I'll spare you the formatting of the plot. I always just look it up anyway, and then even then I play with it until it looks pretty. We've selected 21 features. So here I'm just going to, you don't need to do this again, but just for teaching's sake, I'm going to create a new PCA object and I'm going to define it now with this many NPCs, just like we did in the beginning with 10. Now we've algorithmically decided how many NPCs. So here it is, and then we're going to have to transform the data with this new PCA object, right? So we fit the PCA. I don't need to rescale the data. It's already been scaled by the scaler. So I get the training data in the PCA representation, and I need to do the same thing to the test set. So I scale the test data and then apply the PCA to transform it from the genomic representation to this PCA representation. We print the dimension, so I guess the dimension is going to be something like 30-something samples and 21 features, and then we should get a plot. Okay, yeah, 38 by 21. And yeah, here you look at the number of components, 21, and you can see that the variance explained is going up, right? This is the first principal component explained about 15%, and then the first 2 explain like 25, 30, 40, until we reached 80. Okay, so usually the case is going to be that this is going to have some sort of logarithmic kind of curve. In other words, you're going to get diminishing returns. That's usually the case with PCA. So depending on how fast this curve inflects, is that the right term? The rate, I guess, the geometric rate will determine how quickly you reach like your cutoff here, right? So it's pretty impressive. There's 7,000 features, and by the 21st, we've already gotten to 80. So that means that most of this data is like really uninformative. They're all contributing fractions of a % of variance explained. Okay, so great, we've decided 21. There's only one magic number and it's 80%, but I mean, that's a well-received magic number. It's certainly better than 10, just arbitrary 10 principal components, right? Or 2, why? Because I could plot 2, you know? Okay. So visualize engineered features. Oh, we did this last time. We've now, what do we got here? No loop, NPC. Yes. Where the variance explained, Kim's is less than that. Plus 1. That's great. Shall we try it? I'll try it. All right, this is, oops, is it not copying correctly? Copy. Oh, you're going to make me type it. Okay, good. Okay, MPC is NP where the variance explained, this is over all the, oh, you're applying the cum sum function. Perfect, right? And it's marching along. And when it meets this condition, then there you go. Let's see if I run this. 21, great. You have two solutions, guys. This shouldn't change. This shouldn't change. Oh, okay, so here we left off last time we actually did this. We plotted the distributions. When you're done with all your transformations, you really should do this, right? You should plot the distributions as soon as you get the data, and it's been formatted, like at least formatted, not necessarily like massaged or whatever. But certainly after you're done processing, it better look well behaved, right? So, no value errors. Is it because I did this MPC stuff? Maybe. Let's just load this again. Run this, run this, run this, and then run this. Great. Okay. So there should be 21 principal components, and they should all basically look at least somewhat like a bell curve, right? So that's great, that's great, that's fine, that's fine. They should be like, also the scale here shouldn't be like orders of magnitude. So this is all fine. Shoulders are fine, like this. I'm not going to stress too much about, you know, having these two modes here. This is fine. Yeah, I don't see anything outrageous. So it looks like the data is like well behaved, right? Okay. So at this point, we're done with the data processing, and now we've moved on to feature selection. We've engineered 21 features, right, in the PC representation. Those were picked like completely unsupervised, right? It had nothing to do with the labels. And maybe not all of them are predictive or informative. So let's try some feature selection. I've chosen here Lasso for a few reasons. One, because we've already seen it before. We could have done Baruda or some of the other ones, but I picked Lasso. And the more I thought about it, Lasso is actually the best one. Can you tell me why? Maybe not the best, but a very appropriate one. What does Lasso do? Like, how does it work? How does it do what it does? Yeah, it's a regression. Yeah, it's certainly a regression. I mean, technically we're doing a classification. So you're getting close. How does it do? So, okay, Mert, so it means, least absolute shrinkage. Yes. So what is that? Yeah, what is, like, how does it do its shrinkage, or what is its parameter for, how does it what do you call it? You know, how does it apply this shrinkage? Or how does it go about doing it? What is shrinking? So do you remember in the lecture I showed that sort of plot when we were talking about like ridge regression, right? Where you had this penalty term, right? Maybe you guys can tell me if Lasso was, what kind of penalty term does it use? L1. Perfect. Yeah. It's L1 regularization, right? It's penalizing the features based on just the magnitude of their weights. What the sign to. So the counterpart is L2, right? So maybe you guys can tell me what is the difference between L1 and L2 regularization, or the L1, L2 penalty term, like. You can Google it. Start Googling furiously. Yes. Yeah, L2 squared, right? So in that picture that I showed, it kind of looked, the regression, the penalty term looked like a unit circle around the origin, whereas the L1 looked like a diamond. And I showed that like the concept, what it means is that L1 tends to make the less informative features like tends their weights to 0, whereas L2 minimizes so it can like give you a combination of terms. Anyway, the fact that it makes those terms to 0 makes it good for feature selection, right? It's just says, give me the features that have any weight at after the end of this like lasso procedure, right? Lasso is going to collapse a lot of variables that it finds less informative. It doesn't mean that they're uninformative. It just means there's better informative ones. So I'm going to give weight to that one. Does that make sense? So if I have, certainly if I have, you know, if I have one variable that's informative, one that's uninformative, certainly the uninformative one's going to go to 0. But what Lasso does is if you have 2 variables and it can do, the model can perform just as well using one and collapsing the other one, then it's going to go ahead and do that, right? It doesn't mean that the second one was uninformative. It was just unnecessarily informative, right? I can do everything I need to do. I get the same amount of error using 1 variable versus 2, so I'm going to go ahead and use 1, right? So that's why we use Lasso. But it's getting at now, as a consequence, as a nuance of this, it's getting at why Lasso would be good for this particular set of engineered features. What are my engineered features? I guess maybe we should start there. What what representation am I in? Yeah, we're in principal components. And so what Like what is one of the key features of principal components? Like what is one of their properties? So yeah. So when I described like a PCA analysis, I mentioned something about like you take your features and you compute the covariance matrix, right? Basically, how are my features correlated? And then it does some linear algebra to remove that correlation to give you a set of new features, right? Engineered features who are completely uncorrelated with each other. They are said to be orthogonal, right? So this is very important. And yeah, anybody getting a shot? Like, so why is Lasso going to be good for these principal components? Why not Baruda? Well, forget about Baruda. That's the red herring. So Lasso, when it's doing its regularization, remember how I said that it's going to favor one variable. Well, yeah, it's because they're orthogonal, but it's a little more subtle, right? Like, well, yeah, you're right. So Lasso, given the choice between an informative feature and a less informative one, if it can, if it's unnecessarily informative, in other words, if its information is redundant, then it's go ahead and get rid of that and just concentrate on the one feature. That's how it manifests the parsimony, right? Well, what if you have two correlated features, right? If they're perfectly correlated, then the second one surely is redundant. I know everything I need to know about the second feature by knowing the first because they're completely correlated, right? So one of the sort of features / bugs, I guess, of Lasso is that it will, given a set of correlated features, it's going to pick one out of that set of correlated features. And sometimes that's bad, right? Because if you're trying to decide what's important, it may be throwing away these other features, not because they're unimportant, but just because they're completely correlated, so I could just get away with one. And also, if you're doing this in some sort of repeated, like k-fold cross-validation thing, depending on where the random seed is at time, it might pick a different one. If there's like 5 correlated features, one try it's going to pick one, and the next try it's going to pick another, and the next another, you know. And then at the end, it's going to take all those, like let's say that it was 5-fold cross-validation, right? It's going to take those 5 models and then average their importance. And they said, well, this one was important 20% of the time. This one 20%, 20, 20, 20. So all of these guys, I'm going to assign you an importance of 20%, which may be underestimating their true importance, right? They're all equally important. It's just that Lasso is only picking one or the other. So that's one of the limitations of Lasso, but in this case, it's great because all of my features are orthogonal. They're by definition uncorrelated. So for principal component, Lasso is a great method. Does that make sense? Like what we just said there? Yeah. So so that's one of the tools you get to learn, right? As you do more data science, like if you're working with principal components, like do some feature selection with Lasso, that's a great way. Okay, so that's what we're doing here. We are taking our training data in the PCA representation, and I want to do some feature selection. And so ideally, I want to make some discovery set. I don't want to like, I can use my training data and then move on, and that's actually quite a common practice, but you know, you really shouldn't, like, you know, we selected the features, you know, using the training data, and then went on to like train a model based on those very same features that I selected, and no wonder it does well, because, you know. So I'm going to go ahead and make a discovery set from my training data. So what am I doing here? So X is just the training data. Y is just the labels of the training data. Oh, and I'm going to use train test split here. We've seen this before. To split the data, and I want this test size, that's basically going to be my discovery set. I want it to be 30% of this input. And go ahead and shuffle it. Oh, and I stratify. This stratify function here means make sure that my labels are balanced. And the result is going to be the training, like this new X train, X discovery, which is going to be 30%. Right? So this is 70% of X, this is 30% of X. Y train is going to be 70% of Y, and Y disco is going to be 30% of Y. Right? So that shouldn't be too, you know, arcane. Okay, so now I'm going to, I'm going to go ahead and just get the test set because I'll need it later. Oh, I know why I did it. I did it because you need to like squeeze the dimensions here. So at the end of the day, I have X train, X disco, X test. Y train, Y disco, Y test. That's all that this is doing. Here, we're going to actually do the lasso. So here's where I want you guys to start. Give me the syntax. I need to call the lasso. I need the syntax for lasso CV. I mentioned here that I want to do 5-fold cross-validation, and I want to use the discovery set. So if you guys would tell me what the syntax is for this, I'm very appreciative. Lasso CV, yeah, fit X and fix Y. Yeah, this is just straight out of like a few weeks ago, right? I'm just gonna go ahead and copy your text here. Train the lasso. Yeah, train it. Oh, so yeah, we need the fit. I didn't mention that, but yeah, you're right. Lasso, 5-fold cross-validation. We're going to use a seed here. And not the test set. Not the test set. What should go here? Yeah, the discovery set. Yeah. Yeah. So we're using the discovery set just for feature selection, not for training any model or anything. I just need to know which are what's my parsimonious set of features of these 21 principal components. What's like the best ones, right? What's the most parsimonious set? So lasso is now an object. It's this lasso CV thing. It's been trained on the discovery set by 5-fold cross-validation. Great. Great. Oh, and then I just plot this. I think I cut and pasted this from our previous thing. So that should just print out the things and print out what the selected features are. All right, great. Let's run this. Unmatched. Unmatched. Fit. Oh, okay, yeah, that should work. Unmatched again. What? Oh, disco. X train disco. Is that what it's called? X disc. Oh, did I run this? No. Run. It ran. Okay, so now you run this. Great. So of the 21 features, it looks like it's picked 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Here are their indices. You guys see what I just done there, right? So we've reduced from 7,000 to 21 just by principal component explaining 80%. And of those principal components that explain 80% of the variance, which are the most informative, or what's my parsimonious set of features? And it's these. And you should look at this. for PC, it really should be the first few should be the most informative ones, right? That just makes sense, right? It's picked the 0th and the 2nd. It skipped 1, but that's fine. And then it's picked a handful out here. Great, great. 6, I like 6. 6 features is great considering that we only have 30, something like 36 observations. So we're not terribly underdetermined, right? Okay, everyone follow along what I've just done so far? Yeah. Okay, so now we're going to move on to like the training, right? We've processed our data, we've done some dimension reduction, and we've done some feature selection. Okay, like I mentioned at the very top, there is a missing step in here, and that's model selection, right? So far, I've just decided what the models are going to be. But ideally, what you would do is you'd use the same discovery set, plug in these features onto in a panel of models, and then gauge which models are going to be like the good performers, right? I've just chosen logistic regression, and I've also chosen it to be my benchmark. You always need a benchmark, right? Whenever you do training, at the end of this training or this model development, you're going to have a model, and even if you compare it to like your test set, you can report its performance, but it needs to be compared to, your model needs to advance like the science, right? It needs to advance something. It needs to offer some gain. And so at the end of all of this, you need to do some cost benefit analysis, right? Your fancy model may be, anyway, you can, so to properly do a cost benefit analysis, you need to quantify the gain, right? So, and to do so, you need a reference. Usually this is like what is most commonly done in the literature, right? Or what is the latest model, like the latest industry standard, right? And you need to report the results of your method, your new model better outperform the benchmark, or else it's not worth talking about. And 2, the gains that it makes mustn't be at an overwhelming cost, right? Otherwise, it's not implementable. So I just chosen just a plain old logistic regression to be my benchmark. Now that I think of it, the best benchmark to have used here is probably the results of the published paper. But like burn that into your brain, you always need a benchmark. Okay, so let's train this benchmark, right? So it's just logistic regression, and I've chosen these metrics to look at its performance, right? To quantify its performance. Okay, F1 score. Can anyone tell me what F1 score is? And why I would use it? Yeah, it's like the harmonic average, right, of precision recall. Yeah, so what does that mean? Like why is it important that it's the weighted average? True, like, yeah, you like it's a metric, like just like any other metric. I guess what I'm saying is why not accuracy, right? So simpler, like how many did I correctly classify, over the total number of samples, right? Why not accuracy? Why? What does F1 score have over accuracy? Like, yeah, yeah. Yeah, so like so precision. So precision is like how many true positives, right? I'm making, like how many of the cases I'm catching, right? And if you have really, really low precision, or I guess really high precision, right? It means that not many of the cases are getting by, right? So this is fine, but and recall is like, well, it's the flip side, right? It's the play. It's basically the play between type 1 and type 2 errors, right? That's all fine and good if your labels are well balanced. If there's just as many cases as there are controls, then something like accuracy is naturally going to be balanced, right? It's a good measure. It's a good measure because, like, yeah, accuracy just basically says how many did I correctly classify right? And if everyone is, if like the case is very rare, then I can get a really high accuracy by just saying everyone is a control, right? Nobody's a case. And if the prevalence of the case is like, 0.5%, then I'm 99.5% accurate just by answering B on the test all the way down, right? F1 is the balance between those type 1 and the type 2 errors, right? So it's good for when your labels are imbalanced. And we know this is true for this data set. We showed it last time. I think it was 2 to 1, something like that. Like the AML versus ALL labels are imbalanced. So that's what we're using F1 score. And here's a confusion matrix. You just plot that out. It's like a little matrix. Okay, so I need you guys to define this logistic regression model, this benchmark. So because I just need the syntax for this benchmark. Random state, and then just fit it. Yeah. Yep. Did this work out? I think it worked out. And we're on the training set. Yeah, because we're going ahead and training now. Perfect. Let's see what we actually should fit the intercept. That's my only one comment here. We should fit the intercept. The intercept is the the B0 term. Yeah, this should be fine. And then after it's fit, we're going to display the accuracy. That's just its regular score on the test set, the F1 score, and then plot the confusion matrix on the test set. All right. So, so you see here, 64% accuracy, right? And that's because it's imbalanced. If the labels were balanced, accuracy and F1 score would be the same. This is telling me that this disparity tells me that the labels indeed are imbalanced, and then it's like, this is terrible. This is a terrible score. And here's the confusion matrix. So 19 are cases. Is it 0 then 1? So 19 are the controls, and only one got misclassified, whereas it's just answering everything as 0. It's predicting everything, everything to be, you know, a control, not a case. I think AML was case and ALL was control. And you can tell there's 20 here and there's like 10 here. So it's imbalanced. So it's not great, but that's fine. This is an easy benchmark to beat then, right? All right. Okay. So, so for our model, I just chose this. There's, you could have done a proper model selection process, but I just chosen to do this ensemble method just to show it off to you guys, because it's a easy and really, like, it's one of those tools you always just pull out of the bag. So I'm going to make a stacked model, right? So the idea is I'm going to have a bunch of like base, like mesa models. These base models, they're going to each make a prediction based on the input data. And their predictions go into a meta model. And that meta model is going to make its final prediction based on what the mesa models said. Does that make sense? So I've chosen so that they're comparable. Like, this is a logistic regression model. The top layer, the meta model of this stacked one, is also going to be a logistic regression. But it's base models. You want to pick complementary models, right? So, and this is usually the bag that I pick, right? Let's throw a random forest classifier. It's nonlinear. Let's do a support vector machine, right? That's a linear model. And why not? K nearest neighbors, right? There are a ton, and you could put a ton in here. Like, a proper model selection process would do that. Like, you put in your best performing models in here. So the way you use the stack classifier, and I'll walk you through this bit because we haven't talked about it before, is like the syntax is pretty simple. You just say stacked classifier and you give it this list of estimators. It's going to be in this sort of syntax. And then the meta model is just your final one, right? Your logistic regression. So we know this final model already. It's just this. Let's just put this. Oh, it's not going to be fit. So I think we could just do that. And then the estimators, we need to put in the syntax for each one of these. So let's make them. I'll have you guys help me here. We need a random forest classifier. Okay, and what is its syntax?
I have a quick question about random forest classifier.
Go ahead.
How are you planning to decide the maximum depth?
Yeah, that would be part of your model selection process, right? When you would you could use your discovery set to do some sort of grid search and say how many, like, what is the max depth that is maximizing my AUC, for example, right? And you use that as like the AUC is going to be like the potential for the prognostic potential. But that is an excellent question. Right now, just use the default values, but you really should it'd be part of your model selection process, right? And you use your discovery set for that. Did that answer your question?
Yeah, definitely.
Yeah. Okay. So let's just write the random forest classifier. You could use the default values. They shouldn't be out of like too crazy. I'm gonna look here what I have written. Oh man, I had like an ADA boost classifier. You guys want to do an ADA boost? It's a, do you remember boosting? So boosting is another, you can see here, it's another ensemble method. I'll just talk while you guys are Googling random forest classifiers. Boosting method, like you have a model, it makes predictions, and then of the samples that I got wrong, those get oversampled and then passed into another model, the next model. And so the idea is that the next model tries to, it's trying to improve or boost the prediction on the troublesome sort of samples. It's a bootstrapping method. So you're constantly resampling, but instead of just resampling, like with uniform weighting, you're preferentially picking the problematic samples, right? And so that's how Ada Boost essentially works. So you know what? I'll do that one for fun. So I'm going to put another estimator here, and I'm going to call it Ada, and I guess it's called like Ada Boost, not a capital B, Boost classifier. And what goes in it? I'm looking at, I'm Googling it. Just estimators. Yeah, how many estimators you want? How many times, how many of these, like, it's bootstrapping, right? So how, like, you want to do like 100 or something like that, and a random state. Oh, okay, this is easy. N estimators. Let's give it 100 estimators, and the random state is just our seed. Yeah, that should work. You guys have the random forest? Let's look it up. It's just how many estimators, right? This is how many trees, right? And you know what, you can, well, I don't know, let's do 10. Random state is my seed. All right, let's look up the next one. What is this, KNN? It's called K neighbors. Classifier. Classifier, okay. You guys want to help me with this? And depth. Now let's look up. Max depth. You know what? Like, one of the things that I usually max depth. I try to like if I had to guess, my first guess is always like 3. It's picking one isn't really useful. You're kind of like, you're technically not in the linear regime, but you're just deciding one variable. 2 is by definition, now you're properly nonlinear. And 3, well, okay, now you're getting like, going any more than that, then you start to like lose generality. Like, are you overfitting? And with so few samples and so few features, there's only like 6, right? Wow. So I would maybe even wouldn't even do 3. I'd probably just do 2 because there's only 6. Yeah. In fact, I don't expect a random forest classifier to do very well, in fact, right? There's only, yeah. Okay. You probably get more out of a linear model here. Anybody got like the syntax for the KN neighbors? Did you guys look it up? Random seed, just a random seed, right? Does it need anything else? The number of neighbors. Yeah, no, it needs a number of neighbors. Right? How many? Well, there's only like 30, there's only about like 36 samples. So maybe like 3 neighbors. 5 is a little much, right? Yeah. If you, so you see what I'm saying? If there's like only 30, each one you ask it to have 5 friends, then the likelihood that like everyone's friends with everyone, right? Like that, like it's going to be super averaged out, especially with so few samples. If you had hundreds of samples, then picking 5 neighbors for one, the likelihood that those 5 are shared in common with another arbitrary sample of the other 100 samples. Do you get what I'm saying? You want that. You want them to be sort of like little overlap. But when everyone's friends with everyone, all the averaging like just washes everything out. So I would pick n neighbors to be 3. I also don't expect this one to work too well because there's only so few samples, but why not? Did I spell that right? GHBORS, yeah. Neighbors is like 3, and it has a random number, yeah. Yeah, default is 5. Yeah, I think that's too much. Yeah. Random state. So you like everyone else, like you see what we're doing. We're just Googling it, right? We're just like looking at the syntax and then reading the parameters and making like a decision what makes sense. Random seed is just our seed. That's fine. So support vector machine. All right, let's add this LSVC. Linear. Oh, support vector classifier. That's odd. Okay, let's look it up. You guys have anything for this one? I'm looking it up too. Penalty term. The default is L2 regularization. That's fine. That's the same penalty that's in like logistic regression or like, you know, base regression. The loss hinge. Yeah, that's fine. Yeah, all of this is fine. Wow, this one's easy too. Just a random state. Yeah, just a random state. Okay, so what have I done? What have you done? I just defined a panel of estimators, right? I try to pick ones that are like complementary. In other words, that like they predict in fundamentally different ways. Like I have a tree-based method. I have a nearest neighbor method, a linear method, right, to complement this nonlinear classifier. And we even have a boosting method. I think the base method for this boosting is a tree. So it's like around it's another tree-based method. So maybe they're not that mutually complementary. But this one's boosting. It's going to do it 100 times. Yeah. If it's uninformed, it's not going to be picked anyway by the logistic regression. So now we make this final model, right? The stacked model. It's the stacking classifier, and we pass it the estimators, and then we put the final estimator, the meta model, on top. And we just define it like we did the last one. And now we want to train it. So this thing, I just train it on, I fit it on the training data, and then I display the performance. It's the same performance as accuracy, F1, and confusion matrix on the test set. Okay, so far so good. The closing bracket, of course I did. Of course I messed up the closing on line 9. Oh man, 1, 6, 8, 9 here, somewhere here. Oh, there's that. Yeah. Yep. And yes. Okay, that should work. Another error. Did I misspell neighbors? Random state. Is it not called random state? I'll have to leave early to go to work. Yeah, we're almost done. Yeah. Yeah. Good luck, Serge. Maybe someone can help me with this error here. Is it not random state? Is that what it's complaining about? Extra arguments. What do we got here? Oh, did I write something down? And oh, there's no random seed. There's no random seed here. It's in the docs. Yeah, it is, but it's not. Yeah, but it's saying that it's not in there. And I got another missing one because I just probably erased the closing bracket there. And I got another one. Random state is seed. And oh, estimators. 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 Is that right? Still more? Great. Oh, and this looks the same to me, doesn't it? Yeah. Okay, so it is what it is. So the models have been each individually trained, and then they are passed to a logistic regression, and it makes the prediction, and it's predicting the same thing. Okay. So so now what you want to do is you want to be able to compare our model, our stacked model, and with our benchmark. So when it's binary classification like this, you can always do DeLong's. There should be a big L here. The guy's name. You can use DeLong's test to compare ROC curves, right? Or the AUC actually. Stacked score, not benchmark score. Oh, that's good. That's called cutting and pasting. Stacked. Why did it spell it that way? All right, stacked. Good catch. Great catch. Run this. Great. Much better. They are different. So the F1 score went down. Actually, this performed worse. Well, it is what it is then. And I know why. Okay, so it's performing worse because some of these models are really crappy, right? And this logistic regression scheme, I'm insisting that it considers what each one of these models is saying. And so it has to make compromises to satisfy everyone. And when you have one, I don't know who it is, one that doesn't know what they're talking about, and yet you have to like include them into the into the decision making, your performance will suffer. So this is why it's super important to do like the choose your model, like I said before, right? So the proper thing to do is to have said, I'm going to consider these 4 types of models. I pass my disco set to them, and then I rank their potential, their prognostic potential, right? Doing that probably would have dropped out whichever one is like not helping me out, So yeah, so that's great. So now, and because I just did that, now you have a model that is more complicated and performs even less than just the simple logistic regression. So this is actually a great lesson here. Okay, nevertheless, you can compare these 2 models. You want to ask, are they actually statistically is this accuracy or better yet, the AUC? Is this are they statistically different? And DeLong's test is just that. In R, there's like the PROC package just does it for you. I had to look for someone who has ported this to Python. I'm sure there's a package out there, but like this is the first thing I found, and I guess that's the rule, right? Like faster is better than like the best answer, and this is I found I'll show you guys the code. Some school in Russia like wrote. Okay, so before this, I wanted just to plot out the ROC curves, right? So here I have the benchmark, and this function here, predict prob A. This is the probabilities of the class. You know how like logistic regression, the output is actually a probability from 0 to 1, and then there's a cutoff. It says if the probability is greater than 50%, then you're a case or a control or whatever. So we need to call these two functions, ROC curve and AUC. We would generally look them up. So I think we should do that. Okay, so what I want you guys here to do is call this ROC curve. Look up the syntax and call the ROC curve to predict, to give me the false positives and the true positive rates, because I'm going to need them for the AUC function. And I too will be Googling this. No, it's pretty straightforward. Okay. Just because we're getting close to time, I'm going to start to plow through this. Okay, so when you Google it, you'll find that in sklearn metrics, this ROC curve takes just the two parameters. What is the like the ground truth labels and your predicted labels, right? So I'm using the benchmark predictions. Yeah, exactly. And then the score. Do I need the score? Oh, because I don't understand this last bit. Positive label is 2. We could try it. What do you mean by that, Mert?
I mean, the example I was checking, it was using some type of scores. So I thought we needed. So apparently not.
Yeah, so score is just going to be like the accuracy, right? It's kind of like right up here. That'll just return an accuracy. No, I think the syntax is going to be like the ground truth labels and then just the predictions. And then for the ROC, I need to call the AUC function. Okay, so let's look this up. Let's look this up. Oh, this is straightforward too. It just needs the false positives and the true positives. Yeah, oh, and that's what you wrote, metrics AUC. Yeah, great, perfect. Perfect, thanks, Mert. So the AUC is going to give us a ROC curve, and then we plot it out here. This is your X and your Y, your false positive and your true positive rates. And then I plot the area under the curve. Great. This should work. This is the benchmark, right? Yeah, this is terrible. It's like the area under the curve is like, it's less than 0.5. So this dashed line here on this ROC curve, that is like the result from just flipping a coin, completely random, right? And this orange curve is supposed to look like this, like a curve like this, and that's the like for any given level of type 1 error, what is its type 2 error kind of thing? In other words, what is how are the false positives and true positives related to each other? And when you get a curve that looks like this, then all the area underneath the area underneath that it captures, that is its potential for prediction. Any point under that curve, the model can be tuned to. Ideally, you tune it to like right on the edge, and probably the edge that maximizes the true positive to false positive ratio. In other words, a line, right? Kind of like a diagonal line, and it'll hit a point like over here if the curve goes like that. And that's usually tuned to what's called the type 1 to type 2 crossover point, right? You can march along and tune your model and decrease your type 1 error, and your type 2's grows, and then where they balance out, that's your crossover point. That's where ideally you should tune your model. Okay, but this one is less than 0.5, so it's like worse than flipping a coin. But probably it's not significantly different from flipping a coin. All right, so let's look at, the stack model underperforms, right? So this one's, I gave you the answer here. Okay, if you looked ahead, you could have just copied this part. So here I'm doing exactly the same thing as in this block, only that instead of predicting the benchmark, I'm predicting the stacked model, right? That looks the same. And yeah, so let's plot the curve for the stack. It's 5.2. Okay, fine, whatever. It's probably statistically not any different than 0.5. But now we can ask, is this orange curve statistically different from this orange curve, right? And you will need to do this, especially if you find that your, like the model that you're proposing, like nominally, like technically does have a better performance score, like its accuracy is higher. You have to prove that the amount that it's higher is statistically significant, right? It's bigger than what the benchmark is saying. And you use DeLong's test. So I found this repo here. It's by this, it's this statistics school in Russia, I think. And it's basically, I looked it up. It's the same algorithm that you find in the PROC package in R. So I'm confident it's good. So I went ahead and you can look it up. I went ahead and just gave it to you guys here. So you run it and it's going to load up all of their functions. And what we're interested in is this function here, this DeLong's ROC test, right? It says it computes the log of the p-value for the hypothesis that asks, is prediction 2 different from prediction 1 given the ground truth labels. So the ground truth labels are going to be just the zeros and ones. What are they actually? And the prediction 1 is going to be our benchmark probabilities. Prediction 2 is going to be the stacked model probabilities. All right. So determine if the benchmark and the stacked models are statistically different. Great. What is the ground truth? That's the y-test. What is predictions 1? Just like before, it's going to be the predictions, the probabilities of the predictions of the benchmark on the test set. Predictions 2 is the same thing, but for the stack model. And then you pass it into, I'm asking you to call it, I'll write it out for the sake of time. DeLong's rock test. Well, he gives it to us here. It's just these 3 things. Ground truth 1 and 2. Yes, perfect. Thank you, Mert. Yeah, yes. I think I was nice here too. And I think ground truth, yeah, it's called the same thing. So great. So this is going to return the p-value, right? And then we display the p-value is this. This is actually a catch. I know that it's not the p-value. This is, p-values aren't negative like this. Can anyone tell me why? You can look at the documentation there. Yeah, why is this p-value nonsense? Well, if we look here, it computes the log of the p-value. So I need to exponentiate this to give me something that means something. So it's going to be numpy, not numpy. Yeah, it's numpy. Yeah, that'll work. EXP, right? That's the syntax. I don't want to look it up. I think I'm pretty confident that's right. So if I exponentiate this, I get 0.44. So they're not statistically different. So you would do this when you finish training your model, you compare it to your benchmark, and you better have it better be statistically different, or else it's not worth talking about what the minute differences between your model performances are. This is I can't like say enough how many times I see this in or rather don't see this in papers, and it's very easy to show like performance gain, not performance, like to be like nominally different, what and take your pick of your performance metric, right? And you could find one that like looks really impressive compared to some benchmark, and people are just happy with enough to say that it is better than the benchmark, but you really should prove that that difference is statistically like significant. All right. Oh, just to drive the nail in the coffin, because this is usually my whenever I review something and they don't give me some statistical value, I said like, hey, what are the confidence intervals in that AUC that you have? Right? It's a subtle question, because in doing so they have to do something like this, and they'll find out whether or not it's statistically different. So I gave this to you. This is just you know, just for you, and then you put this in your analysis and then be like, oh, this guy knows what he's talking about. We use the normal alpha value, and you call it the DeLong-Rox variance function. So this, they gave it to us here. It takes the ground truth labels and the predictions for any particular model, and it's going to, like, you calculate your AUC, but it'll give you a 95% confidence interval in that AUC. And if your AUC is like 8, like 0.8, that looks really good, right? But your confidence interval is like, you know, 0.5 to 0.8, something like that, like something ridiculous. You're like, oh, that's, yeah, that's probably, it makes it pretty obvious if like your AUC is just garbage. So, where am I? Oh, okay. I need to copy this variance, right? This function here. Yeah. Yes. Yes. Yes, Mert. Yes, exactly. AUC and COV, we call the function just like you have. Yep. And the ground truth, we already calculated them. And predictions is, I guess, predictions 1. Is that what we said? _1? I forget. Yeah, _1. Okay, so this is going to give me the benchmark stats. I calculate the AUC, and then I print out the confidence interval here. Perfect. So yeah, look at this. This is garbage. The AUC goes from like 0.2, which is like ridiculous, to 0.7. So this model doesn't know what it's talking about. Repeat the calculation for the stacked model. So that's pretty simple. I just cut and paste, right? I don't need the alpha value. And I guess it's predictions 2. Predictions 2. And this is all the same. It's not benchmark, I guess it's the model. model, AUC, and the confidence interval. So yeah, like please do these in your final analysis. This is the step that almost always gets skipped. Like people, you'll just train your model and then you're like, oh, I'm done. You're like, no, you need to like do that last step. This one also doesn't know what it's talking about. It goes from 0.3 to 0.2. It crosses the 0.5 line. Like it means it doesn't know what it's talking about. And those two bars like overlap. So I believe it when it says that they are not statistically different. I mean, this proves it mathematically, but this will show it if you had to put like some bar plot or something. All right, guys. So in the last 4 minutes or so, I'll leave with these last questions on interpretation. So, so I ask here, what does it mean if it's the same as that of the benchmark? Yeah, so what does it mean if our final model AUC was the same as the benchmark? You just shouted. It's kind of self-evident, this question here. Yeah, that's exactly what it means, right? It's not better than the benchmark. It's not worth doing, you know? You need to start over, you know? If you had reserved a testing set and have up until now still only been working with some sort of validation set, and this is just part of your iteration, like, because model development, you never get it on your first try. It's an iterative process. If you've done that, then you can, like, you ask this question, right? Have I beat the benchmark? If not, keep iterating until you've done it, like, I don't know, like 3-5 times, and then maybe you should stop. And also that means, like, before I iterate, I gotta think long and hard. I'm not just gonna like, oh, what if I change the 5 to a 3, or you know, if I change this, like, you really have to stop and think, take a day off, and then think about why it is, how it is that I need to change. I need to fundamentally change what my model is, because I only get a few chances with my validation set. Okay, let's move on. Does this analysis justify using a more complicated model in a future study beyond logistic regression? Well, this is actually a good question. Yeah, what do you guys think? If you read through this analysis and then at the end of the paper they say, so in future studies we're going to try, like, to go beyond logistic regression, try something like nonlinear. What would you say? How would you yeah, how would you critically read that? The linear model is easier to interpret, but I guess if I were to read that, they're implying the problem is nonlinear, and the linear, it's failing because the model isn't good enough. I need a better model, right? And so if they were to suggest, exactly, tree-based, but like in this stacked model, you tried nonlinear models and you showed that it wasn't any better than the logistics. So yeah, it wasn't any better. So no, it is not justified to go beyond logistic regression. And that's a tough pill to swallow a lot of times. People say, like, yeah, in future work, I'm just going to try harder. And you're like, no, you've actually just proven that this is a dead end. Move on. Okay, and what statement about biology can you make? I'm going to skip this one. Short answer is I hate principal components. No, none. In your analysis of the leukemia data from the DREAM challenge, please try a different representation of principal components, because it's black box. It's almost uninterpretable. And I'll leave, since we're at time, and this is kind of a big open question, I'll leave it at that. What I mean by this last question here is, how would you improve it? I don't mean that because this model was no better than linear, it doesn't mean that I can't improve. I could still stay in the linear regime. I think I've convinced myself of that. But I think I can do better than flipping a coin, basically, 0.5. There's a lot of things you can do. I didn't have to pick 80 modes. Sorry, 80. I didn't have to stop my principal components at 80% variation explained. I could have gone to 95. I could have, what else? We didn't do any proper model selection. I think the stack model would have benefited from that. In fact, the fact that it underperformed the linear model means that at least one of those base models is garbage, and it's suffering from that. It has to consider that model. So you probably, if you got rid of it, that accuracy might even go up. Okay, I think that's where I'll leave it here. Next week we will actually go back to lectures, because I'm going to talk about like computer vision and advanced topics, and the week after that is the last week. We'll go over your analyses. I just showed you a complete end-to-end analysis on this toy problem. Just take all of these tools and apply to the hard problem. And I'd love to hear like what tricks you guys employed. At the beginning of every lecture from here on, I'll touch base on how these analyses are going. And with that, I'll just stop sharing. Yeah. Any questions? You guys excited? You're pumped? You're like, I'm going to predict. I'm a prediction machine. All right. Henry, you got any closing marks or?
Nope. I think we're good. Yeah, that was good. Yeah. So if you haven't already, please do the computer vision course on data camp. So I know it's been a while since we've done data camp, but I think that'll probably be a good intro to what Dan will talk about.
All right, guys. See you next week.